Okay, so what I want to do in this video is kind of give you guys a little bit of pre-lab information in preparing to do the KA of a weak acid lab. And so first I'll talk a little bit about the procedure and then why it works. The whole point of this lab is to basically find the KA of a weak acid. Okay, so what you're going to start with ultimately is you are going to, in a little dish, weigh out a prescribed amount of acid, and this is a beaker, and this is a graduated cylinder. And what you're going to do, that looks like a really ugly top hat, what you're going to do is in exactly 50 mils of water, you're going to actually measure with a graduated cylinder 50 mils of water, put it in a beaker, and then you're going to put your solid acid into the beaker and dissolve it. So when you start the procedure, you have dissolved solid acid in here. Your acid in this case starts out as a solid. Dissolved solid. Okay, so let's talk about what's going on in that beaker. When that acid is in the beaker, we have an equilibrium system. So I'm just going to call the acid HA. It's a weak acid. When it's in water, we know that this is what's going on, H3O plus A minus. Okay? So now what we're going to do, once we have, and again, this is going to be 50 mils in that beaker. We're going to use our graduated cylinder again once we've dissolved that solid. We're going to take exactly half. We're going to take 25 mils out, and we're going to put it into a little Erlenmeyer. So we're going to have 25 mils into our Erlenmeyer, and what's left behind in the original beaker is 25 mils. And again, our solid's already dissolved, so we took exactly half of the acid and put it into an Erlenmeyer. You're going to add a couple drops of phenolphthalein, and then you're going to neutralize what's in your Erlenmeyer with sodium hydroxide. So you're neutralizing half of your sample. So what does that look like? What's going on when I'm neutralizing half of my sample? So remember, I have my acid, and I'm going to neutralize an acid with sodium hydroxide. And what do I make when I do that? I make A minus and water. Okay, so if I'm neutralizing this, I am turning all of this into this. So basically, I've taken my 25 mils of this and turned it into, and I don't want to use mils, it's actually not a mil issue, but I'm making sure you understand that every single bit of this has turned into this, correct? How do I know I've done the neutralization in the experiment? My phenolphthalein will turn pink. So I'm going to add sodium hydroxide drop by drop by drop by drop until the phenolphthalein turns pink. At that point, I know that every single one of these became one of these. And now what I'm going to do is I'm going to take this neutralized 25 mils, which is now just that, and mix it back in with my original sample. So what that does, since this was half of that, I have equal amounts now of that and that when I recombine it. And this is the key to this. This is such a sexy little procedure, because by neutralizing half and recombining, I now have assured that my conjugate base concentration is equal to my original acid concentration. Well, who cares? How does that help me find the K of an acid? Let's go back up here. What would the expression be of this equilibrium? It would be H3O plus times A minus over HA. In this scenario, when my A minus and my HA are the same because I just neutralized half of it, my Ka is equal to my H3O plus concentration. So the question is, how do I find the H3O plus concentration? Because if I can find that H3O plus concentration, I can find my Ka, since these concentrations are the same and canceled. So how do I find H3O plus concentration? I don't know. Maybe I'll use a pH meter. So after you recombine these two things together, you're going to use the pH meter and you're going to get a pH. Remember that 10 to the negative pH will give me my H3O plus concentration, which is then equal to my Ka. So that's what you're going to be doing in the lab itself. Again, because we're neutralizing this guy by half, we have taken half of that guy and made the same amount of that. So these end up canceling, and we end up getting our Ka expression to be equal to the H3O concentration. And again, we are looking for the K. All right, so now that we know that, let's take a look at a couple of these pre-lab questions because they seem to be historically causing some issues. So here they're talking about phosphoric acid is a triprotic acid, and then they're like listing all these Ks. And you're like, what the heck are you talking about? Basically, what I want to stress here is that because it's triprotic, we have to remember that phosphoric acid will ionize stepwise. So since there's polyprotic acid. So we're going to lose one H at a time. So we end up with H2PO4 minus plus H3O plus here. The K that's associated with that step is the Ka1 listed up here. And then Ka2 is associated with the next ionization, where we make HPO4 negative 2 and H3O plus. And the Ka that goes with this is Ka2. And then the Ka3 that they're talking about is the final H plus that is removed. And so we get PO4 minus 3 plus H3O plus, and this then is Ka3. So the first question says, write the chemical equation for the first ionization reaction of phosphoric acid with water. I might have just done that. Maybe. Number 2, write the equilibrium constant expression for this reaction. Okay, you know how to do that. You're going to do products over reactants. And number 3 is, what would the pH of the solution be when that equals that? Didn't we just do that? Didn't we say that at the point where these two things are equal, that our Ka is just equal to the concentration of H3O plus, right? So since you know the K, because they give it to you, Ka1, ba-bam, you can then figure out H3O plus, and then, my friends, you can figure out the pH. So that's how you work through the pre-lab question. Now let's look at the post-lab, because that causes some problems. In the post-lab, they give you number 3 is the one I just want to look at for a second. It says the following table lists identities of unknowns in this experiment. Complete the table. And you want to find the pKa. Remember, P is the old-fashioned way of saying negative log. So to get from here to here, pKa is just the negative log of the K. So that's all they want you to do here, is go ahead and list all of your Ks, pKa's, excuse me, and which ultimately ends up being the pH of the solution, right? Because remember, the negative log of the H plus, let me revamp that. If the Ka is equal to the H3O plus concentration, because we cancel that stuff out of our expression, the pKa is equal to the pH, because all we did was take the negative log of both sides. So that's where all of that is coming from. So this is ultimately the pH that you'll see in the lab. So that's how you match it. Whatever pH you get in your lab will be closest to one of these, and that's how you pick the identity of your unknown. Okay? Number 4 says compare the pK values with the literature values reported in question 2. Determine the identity. So that's what you're going to do. You're going to compare the pH that you got in the lab to these pKa's. And number 5 is the one I really want to focus on because kids freak out. It says write a chemical equation for the ionization of each weak acid in the list. Here's where students freak out. Let's list our acids here real quick. We have KH2, PO4. We have KHSO4. We have KH, C8, H8. I can't see that. Is that a 4? And then we have KHC4, H something, O something. I can't read it. And then we have la 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 COOH. So those are unknowns. In 4 of the 5 cases here, these are actually salts that contain weak acids and bases. So the actual reaction that is going on when they say write a chemical equation for the ionization of each weak acid, what you really have to do is realize that this ion is the weak acid and that's just a spectator. So I want you to get rid of all these spectators, treat those as the acids, and I'm just going to do the first one for you, and you're going to react this part of it. This is the part that's the acid, okay? You're going to react that with water, and then you're going to get that second dissociation where it's HPO4 -2 plus H3O plus. So that would be an acid. So again, get rid of your spectators and just write your dissociations all from the actual anions, not including the potassium, because as soon as this hits water, that potassium becomes a spectator and turns into a potassium +1 ion. And this last one, acetylsalicylic acid, better known as aspirin. The ionizable H's are always in the cuckoo-cuckoo is what we call it. When we get to organic at the end of the year, when you get to do some organic naming, you'll see that the acids have this functional group at the end. And the H that's ionized off is only this one. So we lose an H here when we're ionizing. So we take this, add it to water, and we get la 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 COO minus plus H3O plus. Okay? Don't lose H's within here, any of these H's. Those H's need to stay. That's the ionizable H. Okay? And I think that's it. I think that's going to be enough information to get you through the pre-lab and certainly the post-lab. Have a good evening. Bye.